Hamilton.
Wow! Welcome, welcome, welcome. It's good to get started on what's going to be a super action-packed week. This is going to be a really big week. I remember my first reInvent. There was 6,000 people here. I thought it was phenomenal. I learned more than you could possibly imagine. It blew me away in the first reInvent, seeing what customers are doing with the product already. Phenomenal. Just absolutely phenomenal. And so when I see what's here today and here, there's 32,000 people here. Wow! Do you think this cloud thing's going to happen? It looks pretty big. Amazing. Thanks very much for taking time out of your super busy work lives in order to come here to learn about AWS. Thank you for taking time out of your home life to be able to come here and spend a week with us in AWS. Our job is to make sure we deliver enough content for you so that when you go back to work, you're able to get more done, your companies are more successful, and you're going to come back next year. Because we love being able to actually get a little closer and talk in a little bit more detail about some of the things that we're doing. And that, in fact, is what I get to do today. The plan is, just to give you a little background, is we're going to dive in, spend some time on infrastructure, partly because that's where I work, and partly because I think it's super important to understand some of the unique advantages of AWS. So that's the first thing. After that, we're going to have a few people come up and help me and present some other angles, and I'm going to finish off at the end of the show talking about big stuff that we're doing with sustainability and renewable energy. Super exciting. Hope you enjoy it. Let's jump in. I always start with this slide. I'm in love with this slide. We update it, but it doesn't matter. If we never updated it, if we left it the way it was 3 years ago, it'd be wonderful. This is a crazy number. Think what this means. Just imagine, forget about all the innovation, forget about all the things I'm going to talk about today. Just imagine figuring out how to do this. What you need to do is you need to get all the component manufacturers delivering to the server manufacturer. The server manufacturer has to build boards, assemble servers, package them up, test them, push them into the supply chain. The logistics channel has to deliver them to our data centers. Trucks have to back up to the right data center, deliver racks. There has to be enough data center space built. There has to be networking. There has to be power. The server's got to be just installed by technicians, and it all has to be brought up, and then we do it again tomorrow. This is amazing. I'm just shocked at what the team's capable of doing. If I was to think when I joined AWS a few years ago that anything even approximately like this was possible, how would you do it? It sounds like the moon mission. I mean, it just seems impossible. So this is happening every day. If you work with me and say, let's say, is it likely that Amazon uses around the same number of server resources as a Fortune 500 company? My take is they probably use a lot more, but let's just be conservative and say it's about the same. That means we're taking on a Fortune 500 company every day. This is happening. This is happening in a very big way right now. I'm excited by this slide. This is the first time this has been shown outside of Amazon. It originated from actually it was an internal technical presentation done by Brad Porter. I fell in love with it. This slide is absolutely wonderful. What it shows on the x-axis is, of course, time. You can see events happening, Prime Day 15, the fourth quarter, Prime Day 16. See, wow, Prime Day 16, pretty big deal. On the y-axis, it's virtual servers. So we've got virtual servers on the y-axis. They won't let me show you the y-axis. It did exist internally, but I will give you a scale point. I'll give you a scale point. If you walk down there and look at Prime Day 16, that is tens of thousands of servers. Tens of thousands of virtual servers brought online just before they were needed. They delivered the goods, and they were brought offline as soon as they weren't needed anymore. That is a phenomenal piece of news. That is what happens if you get good at managing the cloud. Most workloads, I mean, we talked a lot about elasticity years and years ago, and it turns out the reason why this conference sold out a long time ago and there's 32,000 people here, it's not because of elasticity. It's because it's top-line growth. It's because it allows companies to be agile, to try new ideas, to free up innovation, to test things out without waiting months and months and months to get resources. For things that work, to deploy them quickly, and when something works live, double down, go big, go fast. And that's why people are using the cloud. That alone is probably enough. It also happens to be a heck of a lot cheaper. I'm going to go through a bazillion reasons tonight why it is a heck of a lot cheaper. The funny thing, this slide has nothing to do with any of those things. This is gravy. This is what you get if you're in the cloud. You've taken your workload, you've put it in the cloud, it's costing the company less, the company's actually producing better results, it's a better place to work because there's more things happening, and yet you can still go, as you get better at managing the cloud and start to exploit the unique capabilities, you start to get this type of gain. When you start talking about tens of thousands of servers, let's get a scale point on that. Tens of thousands of servers is a mid-sized data center. That's pretty big. That's a mid-sized data center that came to life, lived for a few weeks, and was brought back down. A mid-sized data center, 150 million, 250 million, ballpark in that area. Think about what this means. Conventional companies running on-premise, what they have to do is they've got to provision to that peak. And because it takes a long time to get servers through the acquisition cycle and actually get them in, actually get them tested, you would never dare run that red line I've shown there. You'd want to bring resources on much earlier, and you'd want to have more resources available because you're very slow to respond to demand signals. And if you're slow to respond to demand signals, what do? You have to over-provision. It's as simple as that. And so you over-provision so many different ways that you've got a $200 million asset. You've committed to it for 3 years, and it does absolutely nothing. This gain is not why this room's full. This is the gain that is available if you start to exploit the unique capabilities of the cloud. That's why I'm excited by this slide. Here's the Amazon regional network, 14 regions all across the globe, 4 more announced for next year. Great news. I love what we've got. We're going to have 18 regions at that point, and these regions are real regions. These are AWS regions. These are not, hey, I stuck two racks in opposite ends of the same data center, and they're relatively independent, and there's a wall between them, so fires are unlikely to spread, and there probably won't be a flood, so those are availability zones. No. Our availability zones are real. They're separate buildings, and they actually do survive through all of those different faults. And I'll show you in detail because I want you to see exactly what the difference is. And the best way to know the difference is to see the difference. Simple as that. 68 points of presence spread out throughout the entire globe. This is the one that's great. You haven't seen this before. I got a question 2 years ago saying, does Amazon have a private network? Do you deploy private networks? Is there any, do you spend on that? A lot of companies talk a lot about it. Have you considered that? Yeah, we thought about it. That is all 100% Amazon-controlled resources. That's AWS. If you're flowing between one region and another, it's flowing on that network. That network is managed by one company. It's not passed from one provider to another transit provider to another interconnection site to another interconnection site. These interconnection sites are wonderful, wonderful, very committed individuals. But my rule is, if you've got a packet, the more people that touch it, the less likely it is to get delivered. It's as simple as that. It's just one administrative domain is way better than many administrative domains. And sometimes on the internet, weird things happen, like one company is not getting along exactly with another company and they're trying to work on a contract, and maybe the resources get a little squeezed during that time to kind of rush the contract along. We're not going to do that. So if it's running on our network, it's under our operational control, we give you better quality of service, and we always have assets to be able to survive a fault. There's no way a single link will ever have any impact on anyone in this room because we have the capacity to survive a link failure and we engineer it that way. Simple. We'd be crazy not to. This, by the way, is not just a little tiny 10 gig network. This is a 100 gig network. Every one of those links that I show you, 100 gig. Every one of them. 100 gig absolutely everywhere. And of course, 100 gig's not enough for many places, and so it's many, many parallel 100 gig links all over the place. So this is a relatively, this is a pretty important asset. When we started this, I've got to admit, I was a little concerned because it's really, really, really expensive. And so I'm concerned. The networking team is 100% committed that this is the right thing to do. From a quality of service perspective, absolutely the right thing to do. And you know something? The team is really good at finding great value, and so these private resources that we have available, they're short-term leases, long-term leases, they're dark fiber that are lit under IRUs, in several cases now, we're laying our own cable, and so everything's available. We'll do anything, whatever's most cost-effective to get the resources that we need to be able to serve is what we do. And because we're not religious about there's one true way and we have to we get good value. Let me show you an example. This is our latest project. This is the Hawaii Trans-Pacific Cable. The reason I wanted to show it to you, the groundbreaking in New Zealand was last week. It's kind of a big deal. This is a Trans-Pacific cable, runs 14,000 kilometers. At its steepest point, it's 6,000 meters below the sea. 6,000 meters below the sea. That's about 3 miles. 3 miles below the ocean. Interesting challenge I can't resist telling you this because I was so captivated by it myself. Every time you get involved with technology, you learn it's always harder than it looks. You know, how hard could it be to string a fiber between Australia and the US? Doesn't seem that bad, shouldn't be a problem. Turns out, signal-to-noise ratios being what they are, you have to have repeaters every 60 to 80 kilometers. That's unfortunate. Okay, got it, I understand. They have to be able to work for 20 years without service. Oh, that's okay, I understand. Oh, and they have to work 3 miles under the sea. Okay, I'm with you. And these repeaters are electrically powered. Oh, that's not good. See, now you've got electrical power 3 miles underneath the sea, supposed to last 20 years, and you've got to get power to it. I mean, those really, really, really long extension cords you see used in some lawns, it doesn't feel like the right thing. So you've got to find a way to get power to these things. And what they do, if you look closely, you'll see the copper sheeting that wraps the fiber. The fiber is actually wrapped in copper. So if you look at it closely, you'll see there's a bundle of fibers, some insulation, and then a couple layers of copper. Now the problem is, these are a lot of repeaters, and so you have to have a lot of copper because it's carrying a lot of current. It takes a lot of power to run them all. And you can't do that. It's not cost effective to do that. So what's the trick? Same trick that gets played on long haul transmission and terrestrial power lines. And that is, if you need a lot of power, you can either deliver a lot of amperage, which means you need a lot of conductor, or a lot of voltage. And of course, they go to a lot of voltage. So the reason why those pipes, those conductors are relatively small is because they're running very high voltage. These devices are running on direct current, and it's actually 10,000 volts positive DC and 10,000 volts negative DC. One more little tidbit, just because I think it's a really interesting one. If you look closely, you'll say, well, there's two conductors. What if one fails? What if someone anchors at the wrong spot? What if a fisherman trawling gets a little aggressive and hopes to catch something bigger? What do you do then? If one of these conductors is open to the sea, if it shunts to the sea, you're down, absolutely down. There's not a third conductor. So how do you have redundancy in this cable? It's a super interesting, wow, I think it is. It's an interesting trick. So you've got 10,000 volts positive, 10,000 volts negative. This 10,000 volt negative shunts to sea, so it goes up to zero. It floats up to zero. So what you do if you're managing the cable is you lift this one to 20,000 volts. Now you still have 20,000 volts heading to every repeater. It's the same voltage level as before, same difference of potential. You're using the seawater as the third wire, if you will. Really cool trick. Go service the cable fault, and then shift it back down to stay the same way again. So in the few times where when you need two, you've got redundancy. Kind of surprising. Okay, what we've got here is back to that beautiful network. I have to show it one more time. Now what we're going to do is we're going to choose one of those regions. I'm going to choose a fully developed region because I want to show you how big it can get and the full richness that's possible inside a region. So dive into a region. Let's see what we've got. First thing we're going to look at is an actual AWS region. This isn't fictional. This isn't what I hope it'll be someday. This isn't, an artist's rendition. This is what's there is actually what's there. So every one of our regions, there's 14 of them worldwide, there's going to be 18 worldwide, every one of our regions has at least 2 AZs. When I say an AZ, I mean a building. We'll come back to that, a separate building. Most of our regions have 3 AZs. All of the new ones we're building, we're going 3 AZ right now. It feels like the right place for us to be. This particular one is 5 AZs. So relatively big from a scale perspective. Every region has 2 transit centers. The job of the transit center is to provide connectivity to the region, to the rest of the world. Our private network, the Amazon Global Network, connects up into transit centers. Customers that are connecting to us are hooking up through POPs or possibly up and through transit centers. Everyone we're peering with through the transit centers. All of our transit providers through the transit centers. And so 2 transit centers is another constant we'll always have. Now we need to wire this up. We've got 5 AZs. The first thing we're going to do is we're going to wire inside each AZ. We're going to run fiber to hook up each AZ. Then we're going to run fiber to hook the AZs up with each other. Then we're going to run fiber to hook the transit centers up into all of the AZs. You see what's going on? There is a lot of redundant fiber here. And the word redundant is a wonderful thing in the networking world because it means when things go wrong, when someone decides to dig a hole in the wrong spot, things keep running. You don't feel that redundancy when you're running, but when you don't read about it, it's because of that redundancy. We've got, in this particular design, in this particular AZ, we have 126 unique spans, which is a pretty substantial number. And get this, of course, many of those strands are more than a fiber. In fact, there's 242,472 strands throughout that 126 links. There's a lot of fiber strands. Here's another interesting little tidbit, at least it caught my interest, is we use 2-inch conduits, so the industry pretty much runs on 2-inch conduits. Well, we're running a lot of fiber between these buildings. Do you want to dig another hole and run another 2-inch conduit? Like not especially. And fibers are small, so you'd think it wouldn't be that hard, but you need to have strength. Otherwise, the fibers will break when they're pulled, so you need to have a core that's strong enough structurally that can last. Second thing is that the whole bundle has to be armored sufficiently well that when the construction workers pull it, it survives, and it's able to stand weather in environments that underground. And so the company that we're working with is really doing phenomenal work. They start in a pretty conventional place. It's very common to have ribbon cables, fibers that are actually in ribbons. And what they're doing is they're taking the ribbons, folding them into a V, and stacking them. And so it forms kind of a V that fills up a quadrant. And then they're doing it again, and doing it again, and doing it again. And by the time you're done that, somehow they get 3,456 fibers. We're the first company to deploy this technology. We absolutely love it. It saved us a ton of money because we're running so much fiber. And you might ask, if you're in the networking world, instead of running a lot of fiber, you've always got a choice. There's other things you can do. One of them is what I showed you back there on the Hawaii cable. That is running, every fiber pair is running 100 waves of 100 gig. You can run parallel waves on the same fiber, and so instead of running 100 fibers, you can run 1 fiber and 100 waves on it. And so what you saw back there was a 30 terabit fiber with 6 fibers, 30 terabit cable with 6 fibers. So why don't we use the same thing here? And the reason is current technology has DWDM or CWDM, that's coarse wave division multiplexing or dense wave division multiplexing, costs more. Just the bottom line is it's more cost effective for short distances to run independent fibers. For long distances, it always wins to run multiple waves on the same fiber. Silicon photonics will probably change that. Our plant will probably eventually end up with running multi-wave. I'm very confident that'll happen, but it's not happening anytime soon. It'll be a little bit of time yet. So almost all of those are single fiber. Not every one, but almost all of them. Okay, let's jump into a fully scaled AZ. Again, remember, this is a specific region. These are actual numbers from that region. Every AZ is 1+ data center. No data center has 2 AZs. No games like I told you. Third one is all redundant network links. We got that covered. Final thing is, I found this one, I should know these numbers, but in fact, it blew me away. We have several, not one, several AZs. AZs are a part of a region, 14 regions worldwide. A single AZ, we have several at 300,000 servers. Wow. Big numbers. Here's a data center. This is one where we kind of go backwards, where a lot of the numbers I show you, I find to be big numbers and surprising numbers and considerably bigger than they were last time I showed them. These numbers haven't really gone up that much. Last time I showed you, I think it was 25 to 30 megawatts. Right now, I'm saying 25 to 32. Almost all of our new builds are 32 megawatts. Why aren't we building bigger facilities? We could easily build 250 megawatt facilities. I've been in 60 megawatt facilities. Nothing challenging about it. You run whatever you want. Here's what's going on. The reason is the same reason we do everything. It's data. We just use the data. And so when you're scaling up a data center, when you're very small and you add scale, you get really big gains in cost advantage. And as you get the bigger and bigger and bigger, it's a logarithm. It just gets flatter and flatter and flatter. And it starts to get to the point where the gains of going to a lot bigger are relatively small. The negative gain of a big data center is linear. And that is, if you have a data center that's 32 meg and it's 80,000 servers, it's bad if it goes down, but we actually have a sufficient scale that you don't notice it. We can work through that. But if you double that, 160,000, triple that, quadruple that, start to get upwards of 500,000. If that goes down, the amount of network traffic to heal all of the problems, it's not a good place to be. So our take right now is this is about the right size facility. It costs us a little tiny bit more to head down this path, but we think it's the right thing for customers. That's a region. Let me show you a little bit on networking. Always have to have my rant on old school networking because it held back the industry for so long. Vertically integrated networking equipment where the ASICs, the hardware, the protocol stack is supplied by single companies. It's the way the mainframe used to dominate servers. And it's actually an interesting observation. If you look at where the networking world is, it's sort of where the server world was 20 or 30 years ago. It started off with you buy a mainframe, and that's it, and it comes from all one company. The networking world's the same place, and we know what happened in the server world. As soon as you chop up these vertical stacks, you've got companies focused on every layer, and they're innovating together, and they're all competing. You get great things happening, and so the same thing's starting to happen in the network world. It is a wonderful place to be. And what's happening is it's going to cause, it's already causing, the ratio of networking to server is going up. In other words, for a given server size, the amount of networking required to support it is going up. And partly it should have gone up before, but networking was artificially expensive, and so server resources were getting stranded. Now, when they're moving to commodity, this is no longer happening. We run our own custom-built networks, routers. So these routers, that particular one happens to be top-of-rack form factor. These routers are built to our specs, and this is the wonderful thing. We have our own protocol development team. When I rant about how poorly served we were by vertically integrated routers, I mostly talk about cost, and it was cost that caused us to actually head down our own path. But it turns out, as big as the cost gain is, and oh my God, it is a big cost gain, the biggest gain is actually reliability. What happens is networking gear is very expensive. Every company has people like me that have big ideas, and they say, oh, I've got a requirement. I'd like you to add some incredibly complicated piece of code to your system. And so they say, sure. And after a while, the networking gear is absolutely, completely unmaintainable, and the next release comes out. They don't test all that stuff that people like me ask for because nobody uses it anyway, and it doesn't work. It just doesn't work. Our networking gear has one requirement from us. That's the only source of requirements, and we show judgment and keep it simple. We actually, it's our phones that ring and it's our pagers that ring if it doesn't work. So it's well worth keeping it simple. As fun as it would be to add a lot of really, really tricky features, we just don't do it because we want reliability. So it's a much more reliable system, and I honestly wouldn't have guessed that. When we headed down this path, I was making excuses saying initially it won't be as reliable. It was way more reliable from day one. Way more from day one. Second thing is, okay, you've got a problem. What do you do? Well, if a pager goes off, we can deal with it right now. It's our data centers. We can go and figure it out, and we can fix it. We've got the code. We've got skilled individuals that work in that space. We can just fix it. If you're calling another company, it's going to be a long time. They have to duplicate something that happened at the scale I showed you in their test facilities. How many test facilities look like that? There's not one on the planet. So it's 6 months. The most committed, best quality, most serious company, it takes 6 months. It's a terrible place to be. So we love where we are right now. We jumped on 25 gig early. 25 gig, it looks like a crazy decision if you look at it. And I was heavily involved with this decision, so I'll defend it. The industry standards are 10 gig and 40. Why the heck would you build 25? It's just like you're asking for trouble. And oh, by the way, 25 was really new at the time, and there's a bit of an optic shortage happening at the time. So it's risky as well. But here's what's going on. If you can't take that, if you're not willing to find a way to solve the optics problem, you have to run 40 gig. So that's where most of the world went. We're confident that 25 is the right answer, and I'll show you why real fast. It's super simple. 10 gig is single wave. That's 10 gig. 40 gig is 4 waves. It's still the same thing. It's basically, it's not quite this bad, but 40 gig is almost 4 times the optics cost of 10 gig. So it's just not a great place to be. 25 gig is 1 wave. It's almost the same as 10 gig. Again, not quite true. It's a little bit more money, but it's almost the same price as 10 gig. And so what that means is on this model, we can run 50 gig, which is more bandwidth, and we get to do it at much less cost because we're only running 2 waves. And from an optics perspective, it's absolutely the right answer. I am totally. We buy enough that it doesn't matter. I mean, the vendors are extremely happy to serve us, and so it's not a problem. But I believe this is where the industry is going to end up. And the reason is, it's whenever you've got the right answer, when it looks that good, it'll happen. And it has happened. We are deploying these by the unbelievable numbers, which is good. I mean, I'm glad we are. Here's the ASIC that runs in our routers today. I am super excited about this because remember I referred earlier to saying, hey, servers went down this path and deverticalized. You can now buy ASICs individually, well, or very large numbers. You can buy ASICs without buying the rest of the gear. We work with Broadcom. This particular one's a Broadcom Tomahawk. It is, at the time when it was released, the most complex by transistor count application-specific integrated circuit there is on the planet. These are monsters. These are absolute monsters. But the beautiful thing about this is a 3.2 terabit part. What does that mean? It's 128 ports of 25 gig. All ports can be running all flat out with no blocking. It'll flow 3.2 terabits at the same time through this. No wonder it's a complicated part. Why do I like that? Well, non-blocking is a wonderful place to be, but the real reason I like it is there's a healthy ecosystem. So Cavium, Mellanox, Broadcom, Marvell, Barefoot, Innovium are all building parts. There's 6 terabit and 13 terabit parts coming. And they will be around the same price in just the same way the server was. And so now what happens is if you separate off basically networking gear has 2 costs. It has this cost and it has optics, and that's basically all there is. All the rest is lost in the noise. What this means is this is on a Moore's Law pace. That is a fantastic thing. Well, optics aren't, but with silicon photonics, they're soon to be heading down that same path, and many of the optics we're running today are in fact multi-chip versions of silicon photonics. So good things are happening. Software-defined networking, big topic today, super important for the last couple of years. We've had it since the beginning of EC2 because you need to have it since the beginning of EC2 in order to offer a secure service as we do. Starting around somewhere in 2011, I believe it was, we made what was realistically a fairly obvious observation, but an important one, and that is whenever you've got workload that's very repetitive and happening all the time, as almost any network packet processing is, you're really better off taking some of that down into hardware. And so what we did is we offloaded the servers and dropped it down, and dropped that network virtualization code down onto the NIC. Lots and lots and lots and lots of gains follow from that. First gain is more resources are available, more cores are available on the servers. Good news. Second gain is things that are hard to read and hard to understand, but they're happening, are little disturbances in the server like flushing TLBs and things like that are now moved off. It's a little bit more secure, considerably more secure. If a hypervisor is compromised, you still don't have access to the network because it's a separate operating system, separate real-time operating system running on the NIC, running all of our software. That's all of our software running on that NIC. And so that offload does wonderful things. Another observation is kind of it's an obvious observation, but a super important one. And this applies to every level of computing, and so it's kind of a nice set of rules to keep in mind. And that is, if you offload the hardware, you run rough numbers, you run roughly a tenth the latency, roughly a tenth the power, roughly a tenth the cost. And so it's a big deal if you can do it. Second observation is people say, hey, the reason why we had to build custom networking gear is you could never have the bandwidth we have in our data centers if we didn't build custom gear. Well, that's not true. I mean, I can give you any bandwidth you want. It's just more parallel links. And I can do it with anyone's equipment. It's not even hard to do. It's hard to pay for if you're using some of these commercial gear, but it's absolutely not hard to do. Do you know what is hard to do? Latency. That is physics. One is money. Physics is harder. Physics, you got a challenge with that. It's just the speed of light in fiber is the speed of light in fiber. And it's just, there may come fibers that are a little bit faster, but it's basically the fastest you're going to go. So latency is key. When you move to hardware, the latency is fundamentally changed. In fact, the way I look at it is I tell software people, your numbers, the things you measure, are called milliseconds. And if you put it in hardware, the things they measure are nanoseconds and microseconds. And so you're changing by big margins. And so this is the right place for us to go. Here's some good news. Here's some great news. Do you believe we're in the semiconductor business? Isn't that great? We're in the semiconductor business. That Amazon Web Services is not only are we building hardware, which I thought was pretty cool, we built this. This is billions of transistors. Billions and billions of transistors. Every server we deploy has at least one of these in it. Some will have a lot more. This is a very big deal. Imagine what we can do if I'm right on those trends I told you on hardware implementation, latency, the cost of power, etc. If I'm right on that point, and I'm fairly confident on that one, what that means is we get to implement it in silicon. So now we've got, in the same company, reporting up into our infrastructure team, we've got digital designers working on this, we've got hardware designers working on the NICs themselves, and we've got software developers. And when you own horizontal and vertical, we get to move at the pace we're used to, we get to make changes at the pace we're used to, we get to respond to customer requirements at the pace we're used to. We think this is a really big deal. And if I'm right, that says that there's going to be an acceleration of the amount of networking resources that are available to servers, then this is a wonderful place for us to be, because we're going to be able to step up to it at a relatively low cost because of some of the decisions I've laid down or outlined to you so far. Good news there. Let's look at this one. One of the things that I do, if you try to manage faults by looking at basically you have a fault, you go post-mortem and you say, oh, I shouldn't have done that, and you learn from it, and then you don't do it again. It's okay. I mean, you should do that. We're religious about it, but I look at other people's faults and try to learn from them. And this one caught my view because, oh boy, I know this fault